Our next unit's focus is going to be predominantly on factoring. So we're going to go through factoring processes, we're going to go through special types of factoring, we're going to go through factoring by grouping, and then we're also going to see how to use this factoring to be able to solve equations. So we're going to start with figuring out what the greatest common factor of something is and talk about factoring by grouping. So we're going to lead into that. We're going to start by talking about what is our greatest common factor. Then we're going to lead into this concept of polynomials, which is something we're going to see very frequently. And then we're going to end with one of our first factoring techniques, which is by grouping. We are so accustomed to right now just multiplying out an expression. So say I take 5x times 3x minus 4. All we've done so far is we've focused on distributing this 5x. So I'd have 5x times 3x for the first piece. And then we'd have 5x times negative 4. So I'm going to put that negative 4 out front times 5x. And then we've gotten accustomed to condensing these. So if we do 5 times 3, that gives us 15. X times x, we add those exponents to get x squared. And then negative 4 times 5 gives us negative 20, and we have a single x. This whole unit is going to be about reversing this process of multiplying expressions. So what we want to do is we want to start with something like 5x squared minus 20x, and we want to be able to put it into that multiplication form. So I want to reverse this process and work in this direction instead. And so that's what factoring is. It just undoes the process of multiplying. What we typically want to do, or the simplest case we have, is we want to take out what's in common to each term. And that thing that's in common is going to be known as our greatest, or so what we're going to start by practicing with is trying to just take out what each single term has in common. Now, unfortunately, this isn't going to be something that we're able to do every single time when we start getting more complicated expressions. But what we want to search for is there something that every single term is divisible by? And if so, then I can take that out. So going back up here, when I start with 15x squared and 20x, if I look at each of these terms, they both have an x, so they're both divisible by x, and they both are numbers that are divisible by 5. So we're able to take the 5 and the x out of each piece to land into this multiplied expression form. The greatest common factor is really the largest value that's common to all of the pieces. And so that's what we want to focus on taking out. So we might be able to figure out a number that each are divisible by, but we want the greatest thing that we can take out of every single term. So let's start with a few examples. Let's factor out what our greatest common factor is, and we're going to identify what that is as well. So if I look at these two terms, I've got 7x and I've got 21. They both don't have an x, so I can't take that out. But 7 and 21 are both divisible by 7. So I'm going to add more steps than I need to in here. But I can think of the first piece as 7 times x. And then the 21 we can break down as 7 times 3. So this way I'm really able to see that they both have this 7 in common. So both terms are divisible by 7. Okay? And so this is what our greatest common factor is going to be. It is exactly 7. So what we do is we take the 7 out, and we want to see what's left over when I do that. So from the first piece, we're left with an x. From the second piece, we're left with a minus 3. Okay? And so we can always check our answer, which is the nice thing about this, because if I multiply this expression out, it should land me right back where we started. So we can check by distributing. If I take 7 and times it by x minus 3, it does indeed distribute out to 7x minus 21. So that is our correct factored form. Now for our next example, if I look at my two terms, I've got 35m and 20p. They don't have a variable that's in common, so can't take any letters out. But looking at 35 and 20, the number I'm thinking of is 5. 5 will divide nicely into both of them. So again, I'm going to try to break this down as best as I can. 35 is 7 times 5, and then we have our m as well. And 20 is 5 times 4, and then we have the p. So I've broken it down as far as I possibly can, and now I can see that they both have a 5 in common. So our greatest common factor is just 5. Okay. And so taking that out, from our first piece, we're left with 7m. From the second piece, we're left with 4p. And if I look at these two terms, now there's nothing in common. 7 and 4, the only thing they're both divisible by is 1. Okay. For this next one, we have a couple different options. And again, we want to pull out the greatest thing possible. So again, this one doesn't have any variable, so I can't take a variable out. However, the 8 and the 16 are both divisible by a couple things. You might not notice the highest number, but maybe you notice that they're both divisible by 2. So if I tried to do that, and I write the first piece as 2 times 4 plus 2 times 8z, we could take the 2 out, and then we're left with 4 plus 8z. Okay. So the problem is, though, I haven't taken out everything, because looking at these two remaining pieces, they're still both divisible by 2, and really they're actually both divisible by 4. So maybe now at this point I notice, oh, okay, there's still something that's in common to both of them. So we can go ahead and write this first piece as, think of it as 4 times 1, and the second piece as 4 times 2z. So now I can also take out a 4, and we're left with 1 plus 2z. And then the front we can simplify a little bit. That gives us 8 times 1 plus 2z. So really all the way back up here, the highest number they're both divisible by is 8. So really a simpler way to do this is the first piece you can write as 8 times 1. The second piece is 8 times 2z. So when I take the 8 out, in the front I'm left with 1, and in the second piece I'm left with 2z. So our greatest common factor is going to be 8 in this case. Okay. So this leads on to our next idea. Everything that we've shown so far is really a polynomial. And all that means is it is a term, or it's a finite sum of terms, where you have numbers, which are going to be these things out front. These are called coefficients. And then you're going to have x to different powers. The key is, though, that those powers have to be integers, and they have to be positive numbers. So you're going to have stuff like x to the 5th, x to the 100th. All of those are acceptable. But you can't have stuff with like decimal powers or fractions or square roots or anything of that nature. So just to give you some quick examples, 5x to the 7th plus x to the 5th plus 1, that's a polynomial. So I have nice integer powers. This last term, you can think of it as x to the 0. So it still has a nice number as a power. Another example is just a constant function. That technically is a polynomial. So it has x to the 0 as its variable term. You can absolutely have decimal numbers in front of the variable, but it's our powers on variables that have to have nice integer numbers. And then -5z is one last example that is also a polynomial. So with these, you can have multiple variables too. We want to be able to figure out what is the biggest thing I can take out from these polynomials. Okay? So we're going to try another example, and we're going to take it up a few notches. We're going to factor out what the greatest common factor is. So looking at this piece, first thing I personally notice is they all have an s squared in common. So I'm definitely going to be able to take that out from every individual term. Second thing I notice, all the numbers that are in front are divisible by 5. So that's also going to be in my greatest common factor. Okay. The hard part is figuring out with these r's, what can we take out? So what you want to do is you want to actually look at what is the smallest value of r you have. So if I look at this middle term, I have r squared. This means I have 3 r's, and this means I have 4 r's. So the most I can take out is 2. So the smallest power of r is r squared. So our greatest common factor is going to have r squared in it. And then also it's going to have s squared, and the numbers in front are divisible by 5. So let's break this down so we can actually see this. We've got 5. R squared we can think of, or r to the third we can think of as r squared times r to the first power, because we would go ahead and we would add those exponents. Then we've got the s squared attached as well. For the next piece, the 10 we can write as 5 times 2. R squared is what we're taking out, and s squared is what we're taking out. And then the 15 we can write as 5 times 3. R to the fourth you can break down as r squared times r squared. And then we have our s squared. Okay. So we can go ahead and take out the r squared from all 3 terms. We can take out the 5 from all 3 terms. And then last but not least, we can take out the s squared from every single term. And so if we take these 3 things out, we need to see what are we left with. From the first piece, we're left with an r. From the second piece, we're just left with a 2. And from the last piece, we're left with a -3 and an r squared. And again, if you want to check that you did this correctly, you could take this and then you could go back and distribute it to all 3 pieces. Let's keep going. Let's try some more. So we've got 10t to the 5th minus 2t to the 3rd minus 4t squared. So first and foremost, I definitely see these numbers out front are all divisible by 2. And if I look at my powers of t, t to the 3rd is my smallest t power. Okay. So this one, t to the 4th, it means I have 4 t's, so I can definitely take 3 of them out. T to the 5th, I can take 3 t's out as well. So let's break this down to make it easier to see what's going to be left. And I'm going to take out a 2 for each piece. So 10 we can write as 2 times 5. T to the 5th we can break down as t to the 3rd times t to the 2nd. For this middle piece, we're going to be taking out both the 2 and the t to the 3rd. So really, I'm going to put a 1 there to remind myself that a 1 will be left over because this term doesn't just disappear. And then in the last piece, we can break down the 4 as 2 times 2. And t to the 4th we can write as t to the 3rd times t. So we're going to take out the 2 from each term. And then we're going to take out the t to the 3rd as well. So our greatest common factor here is going to be 2t to the 3rd. And so we take this out, and what's left in the first piece is a 5t squared. The second piece, we've taken everything out, so really we're just left with a 1. And then in the last piece, we're left with a minus 2t. Let's try one more, and we'll make this one even more complicated. We've got some gross expressions. So we have 3x plus 2 times x minus 4 minus 3x minus 2 times x plus 8. So really looking at these two pieces, they both have this expression in common. So even though it's a more complicated expression, we still do exactly the same thing. This is common to both pieces, so we can factor it out. And then from what's left over, neither of these expressions have anything in common. So our greatest common factor here is the expression 3x plus 2. So if we take this out, I'm going to put some extra big brackets because from the first piece we're left with x minus 4. Then I have this minus sign, and then we're left with the x plus 8 from our second term. And in that second piece, we can keep simplifying more. So if we distribute that minus sign, it's minus x minus 8. And then if we condense, we really have minus x plus x. Those two cancel each other out. We're just left with negative 12. So we're going to put that out front because it's the simpler of the term. And this actually factors really nicely into negative 12 times 3x plus 2, what's known as factoring by grouping. So this is something that's going to pop up. We're going to see that in a little bit. But I do have one more example that I want to do. We've got a polynomial, and we're going to factor it in a couple different ways. We want to factor it first using a positive coefficient, so I'm only going to pull out positive numbers. And then we're also going to do the same thing using a negative coefficient and see how that just alters things slightly. So let's start with our positive coefficient. Looking at both of these pieces, if you take 64 and divide it by 16, it actually is nice. And then if I look at my y values, we have y to the 4th and y to the 3rd. So I can take out 3 y's at most. So our front piece, we can think of that as negative 1 times 16 times y to the 3rd and y. And the second piece, 64, we can write as 16 times 4 with that y to the 3rd attached. So we can take out a 16 and we can take out a y cubed. So this is our greatest common factor. And we want it to be positive, and it is because it is a positive 16. So if we take out these two things, from the first piece, we're left with a negative 1 and a y. And from the second piece, we're just left with a positive 4. So this is really negative y plus 4 times our greatest common factor. Okay. When we deal with a negative coefficient, not much is going to change, but instead of taking out positive 16, we're going to take out a negative 16 instead. So we'll restart by writing our expression. So our negative 16, we're going to think of that as negative 16 times 1. Y to the 4th is still y to the 3rd times y. Now here's where the other piece I have to pay a little bit of attention to. I have a positive 64. To write it with a negative 16, you end up taking out two negative numbers. So negative 16 times negative 4. And then we've got our y cubed. So we're going to take out the minus 16 from both pieces and the y cubed to get the greatest common factor with a negative sign out front being the same as the one above, really. So if we take out the minus sign as well, all that ends up doing is leaving it with a positive y and a minus 4. So taking out a minus sign just flipped the signs on each of these pieces. Okay? So a lot of times taking out that minus can be useful just because it might leave you with a term that's a little bit simpler. So when we're dealing with factoring by grouping, we might have to take out a minus from certain components. So this is our last concept that we're going to go through. And really what's going to happen is this technique is going to be useful first when you have 4 terms. That's going to be where we see it predominantly. But it's also when you may not notice that every single term has something in common. So I can't take like a single thing out of all 4 of my pieces. But what we can do is group individual terms. So the way we're going to go about factoring by grouping is we're going to break apart that expression that we're given, and we're going to group sets of terms so that each group has something in common. We're going to factor out the thing that's common to both of those groups, and then we're going to see, kind of like our example way back up here, we're going to end up with an expression that looks like this, where then my individual groupings will have something in common that we can take out. If it doesn't work, then really you just try again using a different grouping. So for our first example, let's try mx plus qx plus my plus qy. So looking at all of these, I don't have a single variable that's in common to both of them. However, if I look at my first 2 terms, they both have an x in common. If I look at my second 2 terms, they both have a y in common. So what we're going to do is we're going to group the first 2 terms together and the second 2 terms together. Right? So I like to put parentheses around these, because when we have a minus sign in a few examples, we're going to see these parentheses do make a difference. So from our first grouping, they both have an x in common. So we're going to go ahead and take the x out. And what we're left with then is m plus q. In the second grouping, there is a y in common, so we take that out. And again, we're left with m plus q. So both of these now, in these separate groupings, we've been able to identify that they have something in common now. So my first piece has the factor m plus q. My second piece has the factor m plus q. We can now take this factor of m plus q out. And then what we're left with from the first term is x, and from the second term, y. Okay. So this is our process of factoring by grouping. And again, we can still check our answer because we know how to distribute this out. We do need to FOIL. So if we multiply the first terms, that gives us mx. If we multiply the outer term, that's my. The inner term is qx. And then the last term is qy. So comparing that back to our original expression, it's a little out of order, but we get the same thing. Okay. So this is the thing you want to keep in mind with factoring by grouping. If you have 4 terms specifically, and nothing is in common to any of those 4 simultaneously, grouping is going to be the method that we want to use. So let's try another one. We've got 3ma, 3mb, 2ab, 2b squared. So again, typically the first 2 terms and the second 2 terms is what you should try doing. So I'm going to go ahead and group 3ma and 3mb. And then we'll group 2ab and 2b squared. So from the first term, they both have a 3 in common, and they both have an m. So we're going to take out 3m, and what we're left with is a plus b. From the second piece, they both have a 2 in common, and they both have a b. So I'm going to take out the 2, and I'm going to take out a single b. So from the first piece, I'm left with an a. I take a single b out of the second, so I'm left with 1b. And now within this, we have 2 terms. they both have this factor of a plus b in common. So now we can take that out of our expression, and we're left with 3m and 2b. Okay. And again, we could FOIL it to check that, yes, this is the right thing. We get the same thing back, but it is going to be correct. Now let's try a little bit harder of an example, because if you notice, the first two terms are positive and the next two. And it's going to be exactly the same thing for this next example as well. This is where taking a minus sign out is going to be beneficial for us. So I'm still going to try to do the same grouping. I'm going to keep these first two pieces together. And here's where you have to be careful. If you put a minus sign here to take out that minus from the front, typically what happens is we forget to do it from the second piece as well. But if you were to distribute this minus sign back, it would turn this into a positive, which doesn't give us exactly the same expression. So if I put that minus sign in the middle, it's going to distribute to both of my pieces. So this is beneficial for us because now I don't have two minus signs over here, but you have to be really careful with it. Now in each individual piece, I want to see what can we take out. So I made a small typo. That's x to the third. I don't have a number that's in common to both of these, but I do have y squared in common to both of them. This has an x squared and this is x to the third. So the most we can take out is x squared, and we can take out y squared. So from the first term, that will leave us with 2x. From the second term, it leaves us with a plus 1. Now for the second piece, they are both divisible by 7, and they both have a y squared in common. So we're going to take out a 7y squared. Okay. And from the front then, if I take a 7 out of the 14, it leaves us with a 2. It leaves us with an x. We've taken everything out of that second piece, so we're left with just a 1. And so this should happen every single time. We now notice that they both have this 2x plus 1 factor left over. So if you don't end up with the same factor in each piece, there's a good chance you didn't take the full greatest common factor out of the individual groupings, or you messed up with a minus sign somewhere. So just double check those first. But now they both have the 2x plus 1 we can take out. From the first piece, we're left with x squared y squared, and then we're left with this minus 7y squared. And now technically at this point, if it said to factor completely, we wouldn't be 100% done, because there's one thing I didn't check at the beginning. They all have a y squared that's actually in common. So maybe you don't notice that because you saw the 4 terms, and that's perfectly okay. When I get down to this step, they both have a y squared. So I can actually keep factoring. So that's 2x plus 1. We can take out a y squared, and then we're left with x squared minus 7. So now it's as far as we can possibly factor. I'm going to go through number D now. And so first thing I'm going to do, because the last example we saw there was something that was in common to all of those pieces, we can make our lives a little bit easier right now by recognizing that there is an m squared in every single term. So I'm going to go ahead and factor that out first to leave us with 3n squared plus 15n minus 2n squared minus 10. Okay. And now we're going to do the factoring by grouping on this remaining piece, and that m squared is just going to stay out front. So I'm going to group my first two, and unfortunately this does leave us with lots of parentheses because that m squared has to be distributed to everything. So our first grouping is just going to be the first two terms. I'm going to take out that minus sign to leave us with 2n squared plus 10. Okay. And then I'm going to even show, we're going to break this down a little bit more. From my first piece, both these numbers are divisible by 3, and they both have one single n in common. So we can write that as 3n times n squared, and then we can write this as 5 times 3n. For the second piece, they really just both have a 2 in common. So I'm going to break down the 10 as 2 times 5. So what that does is we can take out 3n from the first term, and that leaves us with n squared plus 5. And then we can take out a 2 from the second term, and it also leaves us with n squared plus 5. Okay. So we took out the 3n, then we took out the 2. Now looking at these, they both have this factor of n squared plus 5. So we can take that out. And then we're just left with 3n from the first term and minus 2 from the second. So in our next section, we're going to learn different processes of factoring, and we're going to start with factoring something of 3 terms, and that's going to be reversing our FOILing process.